Welcome to the Real Science of Star Trek's Warp Drive. In October of this year, 2025, National Geographic published an article that excited every sci-fi fan. You can find a link to this article in the description below, but in this video we will be discussing how close we are to a real working warp drive. For decades, warp drive has been the ultimate dream of Star Trek. A way to reach other stars, not in centuries, but in hours. And now, physicists are actually publishing papers that show it might just be possible. But how close are we really? Could a real warp engine ever exist? Let's break down the latest research, the numbers, and what the real science of warp drive actually looks like. In the Star Trek universe, a ship doesn't travel through space the way a rocket does. Instead, space itself moves, compressed in front, expanded behind, carrying the ship in what's called a warp bubble. It's a clever storytelling hack. Inside that bubble, you're not technically breaking the speed of light, because the ship itself isn't moving faster than light locally. Space is doing the moving for you. In Star Trek, warp 9.6 equals approximately 1900 times the speed of light. That means a trip from Earth to Alpha Centauri, our nearest star, which would normally take over 4 years at light speed, would take just under a single day at warp 9.6. That's the fantasy. The physics, though, begins in 1994. In 1994, a Mexican physicist named Miguel Alcubierre shocked the physics community. He found a solution to Einstein's equations that described exactly what Star Trek imagined, a moving bubble of space-time contracting in front and expanding behind. Inside, the spacecraft could sit still, locally obeying every law of relativity, while the bubble itself carried it forward faster than light. It was the first mathematical model of a warp drive. But there was a huge catch. It required negative energy to work. And not just a little. The early calculations suggested that to move a bubble about 100 meters wide, you'd need more negative energy than the total positive energy of the entire observable universe. That's more than everything that exists. That's like asking for an antimatter fuel tank the size of a galaxy. Even worse, if you tried to turn it on too quickly, quantum theory predicted that the bubble's edges would explode with infinite energy. A kind of space-time shockwave. So in short, the math worked, but the universe didn't. Negative energy isn't science fiction. It's real, but tiny. The Casimir effect, for instance, produces a minuscule amount of negative energy between two metal plates, nanometers apart. But scaling that up to power a starship is impossible with any known technology today. In the Alcubierre model, you need something like 10 to the power of 67 joules of negative energy. That's a 1 followed by 67 zeros. For comparison, the entire output of the Sun, over 10 billion years, is only about 10% of that. So, in the 1990s and 2000s, warp drive theory was dismissed as a beautiful mathematical toy, but impossible in practice. Then, in 2021, physicists Alexei Bobrick and Martire revisited the idea. They published what they called a physical warp drive, a model that reshaped spacetime without violating any of Einstein's laws, and, crucially, without needing negative energy. The trick was limiting the warp bubble to subluminal speeds, i.e. slower than light. In their design, the bubble still distorts space, but never enough to break the light barrier. Their calculations showed it could, in theory, be built with ordinary matter. The catch, the energy cost is still staggering. To move a small bubble a few meters wide, you'd need the mass of several Jupiters, around 10 to the power of 27 kilograms. That's about 1,000 Earths. But for the first time, physicists had a model that didn't require exotic matter. Warp drive was still out of reach, but no longer forbidden by the universe. Then, in 2024, another leap forward was made. A team led by Jared Fuchs and Martire went further. They unveiled what they called a constant velocity physical warp drive, Their equations satisfied all of the classical energy conditions, meaning it could be built entirely from positive energy matter, nothing exotic, and the geometry of their warp bubble couldn't be dismissed as just a coordinate trick. Like the Bobrick model, it still travels slower than light, but the implications are huge. It shows that a warp-like space-time manipulation is mathematically possible, within general relativity. No magic required, no violations of physics required. The recent National Geographic article focused on this exact shift, the move from impossible fantasy to theoretically allowed. As the article puts it, warp drive may no longer break physics, but the engineering remains beyond imagination. Imagine placing your hand on a soft rubber sheet. Press down in front of a coin to compress it. Stretch behind it to make the sheet expand. Now the coin stays still relative to its bits of sheet, but the sheet itself moves the coin forward. That's essentially a warp bubble. The ship doesn't move through space, the space itself moves around the ship. Inside, everything feels normal. No crushing acceleration, no time dilation. Outside, distances shrink and expand as the bubble glides by. It's a true superluminal version. The front of the bubble would be contracting space faster than light could move through it, so light would never catch up to warn what's ahead. Unfortunately, that's where causality breaks, and where most physicists would draw the line. So what are the remaining real science problems left for warp drive? 3 words: energy, stability, causality. First, let's talk about energy. Even in the most optimistic positive energy models, you'd need at least the mass of Jupiter, and that's just to move a microscopic bubble. To carry a ship the size of the Enterprise, you'd need a mass equivalent to the entire Milky Way. Second, stability. Quantum field theory predicts enormous vacuum fluctuations at the bubble's boundary. If the bubble wall formed too quickly, the energy would spike to infinity. You need to ramp up the field gently, perhaps over hours or days, just to avoid self-destruction. The third problem, causality. Anything moving faster than light risks creating time loops, situations where cause and effect can reverse. Some mathematicians have proven that superluminal warp drives naturally allow closed time-like curves, meaning you could, in principle, arrive before you left. That threatens to break physics. It also threatens to break logic. As of October 2025, the field has matured. There are now roughly a dozen peer-reviewed papers each year exploring new warp metrics. Some investigate ways to reduce the energy by changing the bubble shape, a narrow neck in front, a ballooned region behind. Others simulate how gravitational waves might ripple if a warp bubble collapsed. In theory, such a collapse would release a burst of gravitational energy that detectors like LIGO might one day be able to pick up. And the National Geographic article points out something important. This isn't about building a spaceship next year, it's about testing the limits of general relativity, pushing Einstein's equations until they almost break, to see what they reveal about space-time itself. Even if we never build a warp engine, these ideas matter. Studying warp metrics teaches physicists how space-time behaves under extreme stress, how energy conditions shape gravity, and maybe even how quantum gravity will one day unite with relativity. NASA's own research teams once tested a tiny warp field interferometer to look for space-time distortions on microscopic scales. They've had no luck yet, but the principle is simple. If we ever detect a measurable warp bubble, even on the scale of an atom, it would change physics forever. And there's another reason to care, the dream itself. Star Trek inspired generations of scientists, from astronauts to engineers to theoretical physicists. Warp drive represents one of the ultimate symbols of curiosity, our refusal to accept that the stars are forever out of our reach. So, can we build a warp drive? Realistically, not with any technology we can imagine today. But it's no longer fair to say that it's impossible. Alcubierre's model broke the rules. Bobrick and Martire rewrote them. Fuchs and his team showed the rules themselves are more flexible than we thought. As the National Geographic article recently summed up, warp drive no longer belongs only to science fiction, but the laws of physics still demand a steep price. That price is energy, engineering, and an understanding of space-time far beyond what 21st century scientists currently possess. But the fact that the door isn't fully closed, that's the most exciting discovery of all. So, what do you think? If scientists ever found a way to bend space itself, even just enough to move a grain of dust, would it still count as warp drive? Or is faster-than-light travel destined to remain pure science fiction? Drop your thoughts in the comments, and if you love seeing the line between real science and science fiction blur, don't forget to like and subscribe. I'm Dr. Dan Stokes, and this has been the Real Science of Star Trek's Warp Drive.